Okay, welcome everybody to ECON 201. This is the first section of week three. So let's just get right into it. I'm going to start with a little reminder for you guys. So chapters 8 and chapters 9 for the reading quizzes. Those are due Sunday at midnight. That's really what you have to worry about this week. Next lecture, I'll be talking more about the first writing assignment, just kind of getting you guys maybe a little introduction as to what I expect and how this process goes. That'll be due after the first midterm, but I do suggest getting that in as early as you can, because now you have all the tools you need to essentially finish that writing assignment. So you may as well get a head start, so you don't have to worry about that after the midterm. Okay, so today we're going to focus a lot on growth, how economies grow, what growth is great, a bunch of all this other stuff to deal with growth. The first part of this lecture, we're just going to pretty much look at a ton of pictures. So we're going to look at real GDP growth rate in this graph in 2018. Remember, real GDP, we say it's real GDP because it's growing and or the GDP, we're looking at how that grows, but we're factoring in inflation. So if your inflation is super high, your growth rate might actually turn out to be negative. We see that in a couple countries, like right there, we have negative real growth rate. And for the United States, it's a nice light green color, which means it's like 1 to 2%. That's pretty standard. I'll note that like China, India, I believe that's Mongolia above China. These have grown pretty quickly over the last couple years, mostly due to policy, along with just them developing as a nation. So I guess just typically when a country first gets introduced to a bunch of new technology, they're going to grow really fast, and then as they become more established, the growth rate will decrease. And it as the United States, using that as a good example, or maybe just all of Europe, it kind of settles down to somewhere between like 3 or 1 to like 4-ish%. Usually we think like a good growth rate for the United States is around like 2 to 3%. And again, this is real GDP. Here is another graph. We just have different axes as before, so the colors are less defined. And now we're looking at 2016. It kind of paints pretty much a similar picture, with a couple exceptions. So today, like I said, we're talking about growth. So we're going to talk about what determines output in the long run. And for now, we're going to kind of ignore the business cycle that we talked about in week two. We're just throughout the business cycle. Again, remember, let's plot like real GDP, and this is time. So we know things go up and down through the business cycle, like so. What we're really going to focus on is this line um, that we draw straight through the business cycle, and that's as real GDP rises over time. If we measure the change in this real GDP, this would be the growth. So maybe from year 2009 to 2010. We'll talk about why are some countries rich, why are some poor, why do poorer countries tend to have higher growth rates? So will they catch up? And then we'll talk about something called the convergence hypothesis. Okay, so for most of human history, everyone everywhere was extremely poor. Today, we see less developed places like Chad or Nepal fare better on essentially any indicator of development than like England in the 1800s. So here's just a couple metrics on development and we're talking a lot about growth today, but there's a lot of other things to consider when we're talking about how well an economy is doing. So England in the 1800s had life expectancy in the 30s. The infant mortality rate was fairly high. Um, and then the literacy rate is near to zero. Okay, so all of these things go into how we evaluate a country, even if a country is experiencing really high economic growth, but the literacy rate is still zero. That's not exactly the best case scenario. So yeah, okay, here's a graph, and it is GWP, which is the gross world product. So we're talking about maybe the gross domestic product, which is GDP. That's of a certain country. This is of the entire world. We see that it was, remember, this goes like all the way back to minus 1 million BC. Um, and around like 1850 is really when we started to see big growth. That was due to the Industrial Revolution. And since technology has gotten better, um, it's just increased year over year at kind of an exponential rate. Here's real GDP per capita, and we're pinning this real GDP to 2010 US dollars, which is why that's in the title here. And again, we're starting like from before the United States was even a country, which is probably like I think that date is like 1720 or something. Um, whoa. And you can see the United States has grown and kept growing, and it still grows to this day. What's key here is we're talking about GDP per capita. So as we have grown as an economy, we are also taking into effect that our population has grown. Okay. And I think currently the United States GDP per capita is around 63K. I could be a little wrong with that number here. Also note that like the axis is here, these go by every 100 of years. So it's we can spread this out and maybe that's a better look at the graph. This looks more since like the United States was founded. Okay, so next graph here, we're looking at the world population living in extreme poverty. Extreme poverty is a metric that is measured where people's income is below a certain threshold. Um, so as you can see, like in the 1820s, 1840s, 1850s, we had a lot of people in extreme poverty. That's because during this time you had a bunch of people that made near to nothing, and then along with that, you had a few amount of people that made a ton of money, right? Um, as since like the 1920s onwards, you see this trend kind of decrease where we are today in the world in 2015 is the last metric that we have, where there's more people not in extreme poverty than people that are in extreme poverty. Now, this is a good thing, um, but again, with all these graphs, it's very important to kind of look at exactly what this is saying. We're putting people into two groups here. So this is living in extreme poverty and people who are not in this extreme poverty group. So simply because we are right here, this does not mean that inequality has greatly decreased because we're only looking at the binary number here. Okay, or binary group. Here's another graph that kind of says a similar story. While this one was focused on the number of people, this second graph looks at the share of people, which is why these are in percents on the y-axis. And you can see the general trend where the people that are in extreme poverty, the share of them has decreased as time has gone on. And again, this is We're looking at a world metric here. Okay, so now we're going to kind of split it up into a couple of groups. And again, we're looking at the same thing. So this is the reduction of extreme poverty in countries that we consider to be rich today. On the y-axis, we have the share of people living in extreme poverty. And you can see the same kind of trend that we saw in this graph right here, where the share of people living in extreme poverty has decreased. Here's the world. Here's Japan, Italy, Australia, New Zealand, and the United States. So interestingly enough, Australia, New Zealand, and Canada have decreased this share significantly, a lot quicker than even Japan, Italy, or the United States. Um, so yeah, there's just a couple metrics, couple tables to show you, graphs to show you guys. Not too much to get into past these pretty pictures. Okay, next we're going to compare the economies across the time and space. So now we're looking at real GDP per capita. Remember, per capita is adjusted per person. So it's the amount of GDP per person in your country. We have the United States, China, and India on this graph. So China, as a developing nation, you can see their trend is they have increased their real GDP per capita significantly since, say, 1980, 1990. India has also faced this nice increase as they become more developed. The United States is a little more constant in this. One thing I'll kind of note is this area right here. So, as you probably this is not cooperating today. I'll know that during the Great Depression, it was a bad time. GDP decreased, real GDP per capita also decreased. And then due to World War II, where we are making a ton of military equipment, the government is getting involved in producing all of these arms, tanks, jets, all of the above to help in the effort of World War II that boost our economy because we're simply producing more goods as a nation. And then past World War II, it kind of declined a bit, and now we're back on like a similar trend as to almost what we were prior to that Great Recession, World War II bubble. So a lot of people attribute like the United States really getting out of the Great Depression as World War II was a great help to the United States. It's for this reason. So the United States had to produce a lot of things during World War II to help in that effort, and that boosts our GDP as the government intervened a lot to produce a lot of weapons to help out in that effort. Okay, next thing we're going to look at is the income per capita around the world. This is kind of just an indication of the nations that are doing better than others, nations that are more developed, such as Europe, United States, Canada, and Australia, are in the dark blue, so they're in the top section here, and then nations who are in lighter blue or even white have lower income per capita around the world. Okay. And so along with this graph, so let's kind of like go through this a little slowly. You see the like Africa, even China, they had pretty low income per capita. However, when we look at economic growth, we see that the people who had low income per capita experienced high economic growth. And then this works both ways. So the United States had really high income per capita, but their economic growth was a lot slower. Same with Canada, same with Australia. Okay, so this is kind of like a theme that we see in data. There's going to be a model that we use that will kind of explain why this is going on. Okay, so let's talk a little about the change in levels versus the rate of change. So when studying economic growth, it's important to understand the difference between a change in a level and a rate of change. When we say the real GDP grew, we mean that's the level of that the real GDP increased. And so sometimes that's useful. However, sometimes it's more useful to look at the rate of change of the GDP or the growth rate of the GDP. So those two things, we can look at the United States, which has it's a big economy. We have a high GDP. Saying that our GDP increased by, say, 10 million tells a different story than saying if Sudan increased their GDP by 10 million. So that's why the rate of change is usually a more useful metric in figuring out the actual growth of an economy. So here's an example. Might say the US real GDP grew during 2010 by 385 billion. If the US real GDP in 2009 was 12 billion, then real GDP in 2010 was 13 billion. So we could calculate the rate of change or the growth rate of the US real GDP during 2010 as this number, which comes out to be 3.03%. And I'll just a helpful reminder when we're kind of finding these like growth rates, the same formula will be used throughout this class. It's also just like a percentage change metric. So for any type of percentage change that you're looking at, you can always use this formula. The formula that was taught to me is you take the new minus the old over the old, meaning the new, in this case, it's the new GDP, so 2010 minus the old GDP in 2009 divided by the old GDP in 2009. You multiply that by 100, and that's how you can get the growth rate. So it's kind of a useful formula to know. Um, yeah. All right. So growth rates. How did the United States manage to produce more than 7 times more per person in 2010 than in 1900? Let's take this a little bit at a time. So, long run economic growth is normally a gradual process in which real GDP per capita grows at most a few percent per year. So, from 1900 to 2010, real GDP per capita in the United States increased an average of 1.9% each year. And this is it says each year, so that means the average growth from 1900 to 1901. 1901 to 1902, and you go on, you add all these up and you divide them by the number of years. That's how we got this metric right here. All right, so we do have this nice little formula. It comes empirically, we've kind of derived it. It's a good tool to have. It's not exactly perfect, but the rule of 70 tells us how long it takes real GDP per capita or any other variable that grows gradually over time to double. And this is the formula that we use. So it's the number of years for a variable to double, and it equals 70, which is why it's called the rule of 70, divided by the annual growth rate of that variable. Where do we come up with 70? It's just kind of a good empirical rough estimate. There's nothing more beneath it. It wasn't like found to be perfect. The actual number is usually not 70, but it's a good round number that we can use. So that's the rule of 70. We'll show you how you can probably use this. So let's look at China. China grows at 10% per year for about 35 years. We can use the rule of 70. So again, the rule of 70 is going to say we take 70 divided by the annual growth rate, and that's going to tell us the number of years for the GDP to double. We apply that to China. Given their 10% per year, you take 70 divided by 10, and that gives you 7. So it says that we're doubled every 7 years. Okay. Um, and then if now we can kind of work with this equation a little bit. So for example, we can multiply the annual growth rate and divide by the number of years for the variable to double. Alternatively, We can take 35 and divide that by 7 since we know that it's going to double every 7 years. And 35 divided by 7 says that this GDP will double 5 times in 35 years. Um, and so when you double something, it's multiplying it by 2. 2 to the fifth tells us that the economy is 32 times bigger over 35 years. Okay, so let's look more closely maybe at the United States, actually go through this exercise. So United States averaged more like 2% over that time. The time again is 35 years. So using the rule of 70, I'm going to take 70 divided by the growth rate of 2, and that gives us 35. So this tells us in 35 years, GDP should double 1 time. So the next step is you're going to take how long it takes, how long we're looking at, which in this case is 35 years, divided by how long it takes to double the GDP, which we found to be 35. It's very convenient. And so this gives us 1. So it tells us that the GDP should, or the growth rate of the GDP should double only 1 time in the 35 years. So when something doubles, we say it's 2 to however many times we're going to double it. In this case, it's 1. So that tells us that the United States over 35 years should have a GDP that's 2 times bigger than it was 35 years ago. Very nice. Okay, so next let's look at the cross-country comparison of growth rates. So we are looking from the average amount of the annual growth rate from 1980 to 2010. So China, it grew a ton. It's the winner. United States, it's about 1.7%. India has grown significantly. They kind of followed a similar trend to what China has done in their timeline in development. And then we look maybe over at the lower ones like Argentina. They've had a bunch of struggles as of recently getting their inflation under control, which has caused their GDP to decrease recently, actually. And then Zimbabwe also kind of had a bunch of economic factors impact them, which means their growth rate has decreased. Okay, so we see all of these empirical things, and as economists, we kind of want to understand, for example, why is China's GDP growing at an average of 8.9%? Why is the United States only at 1.7%? What's driving this? What can we attribute to all of this? And so this is kind of where models are going to help us out. So economic models give us an intuition that help explain empirical results that we found. I showed you at the first half of class a bunch of empirical results. Now we're kind of going to get into a model that maybe gives you some intuition over what's actually driving this change in GDP and this growth. Okay, so the variables that we have, Y is considered to be output, or we can call it real GDP. And then L is the labor force. So we talked about unemployment last week. You know what a labor force is. So L is labor. And then Y over L is labor productivity. So we can think about it as the real GDP per worker. So how much does one worker contribute to the GDP? So this is, yeah, and that's how we define technically GDP per capita. So we can write this equation like this, where Y is going to equal L times Y over L. Why can we do this? Well, if we simplify, we can cancel out the L's and it just gets Y equals Y. So this is just mathematically a true equation. We're just going to add in L up here and down here, and that's going to kind of help us out with this model in a way. So how is L determined? Well, it's determined by the labor force participation. along with the demographics of how many people are in the country, how many working people you have, all of that above. So the sources of long run growth, one is labor productivity. So that's referred to simply as productivity is the output per worker. We're going to talk a lot about this. So, for example, let's start by looking at why this is important. Well, let's go back to the theme, I guess, of this class, which I always go back to, is this pizza kitchen. If I am to hire one worker for my pizza kitchen, however, I do not have a pizza oven. Instead, I have just a conventional oven, and it takes him 40 minutes to make one pizza. His productivity is okay. He can still make pizzas, but it's not very high. Now, if I have an industrial grade pizza oven that he can use, well, his productivity is going to increase significantly because now he can put pizzas in, take them out a lot faster. The quality of the pizzas are probably way better because pizza ovens are great. So long story short, technology or the capital that you have. Remember, capital is kind of like equipment that labor uses. This can impact productivity. Um, so that would be right here. That's physical capital. That an example of that for our case is like a good pizza oven versus maybe a terrible one or a conventional oven. Another determinant of labor productivity is going to be human capital. So, human capital, a good example of this would be education. If my workers are very educated, we assume that they can produce at a higher rate because they are more knowledgeable about what they're supposed to be doing. And lastly, it's kind of just like technology. So, technology is technical means for the productions of goods and services. So a lot of things drive improvements in technology. Recently, it's kind of been AI is the buzz, but also we can go back to the Industrial Revolution. So the Industrial Revolution improved worker productivity because now they have access to all these things they didn't have before, which means that when they work, they can produce more in a shorter amount of time. Okay, so we have this aggregate production function. So this aggregate production function is going to be the framework that we're going to use. It's going to show how productivity, which is again, productivity is the real GDP per worker, depends on the quantity of physical capital per worker and human capital per worker, as well as the state of technology. So this is a pretty common thing that we use in economics. We say, okay, we want to study labor productivity. What are some things that we know will drive labor productivity? We have our 3 bullet points right here. Okay, so now we're going to make a function where labor productivity, which remember we defined as Y over L, this is going to be a function of this is your physical capital, and it's your physical capital, and we're dividing by the labor. So how much physical capital does each worker have? Human capital, right here is given by H, and then T is technology. So we assume that technology is more or less independent of how much labor you have. Everyone has access to this technology, so we don't need to divide that one by labor. Okay, so now we're getting more into modeling, which is something we do a lot in economics. We have this production function, so we say, okay, aggregate production is a function of these 3 inputs here. Let's quickly go over like what is a function, what does it do? Okay, so a function, it's a tool. It takes in a value and spits out another value. So in this case, we would say x is a function of y, meaning I want to point down here. For those who are just kind of getting into college maybe or haven't brushed up on math in a while, we can write all functions like so down here, where pretty much how this works is I am going to say plug x equals 0 into my function. And when I do that, I know it's 4 times 0 plus 2, which equals 2, right? And then I can plug in a different number into my function. And now this spits out 6, right? So this f takes the place of this y. So we say like y equals f of x, and then f of x is defined by this relationship right here. So that's kind of the same thing that we're doing with this production function. We'll say y over L equals f of, and then we'll just plug in numbers. So maybe this is 1, 2, and 0, right? And that's going to spit out a number for us. Okay. Okay, so yes, that was a function that we learned before with only one variable. Well, functions can have multiple variables. So we look here, this is y equals f of x and z. We also say that x and z, these are inputs, meaning we plug them into the function to determine y. So if we look at maybe f of 1 and 0, that means I plug in 1 for x and 0 for z, and then that will, spit us a number of 6 as well. Very nice. Okay, so when we account for growth, we have this aggregate production function. So a recent example of an aggregate production function applied to real data comes from the comparative study of Chinese and Indian economic growth by the economists. There they are. And they use this following aggregate production function. So we have GDP per worker. So GDP per worker, remember we defined it as Y over L. This is a function of technology, physical capital per worker, which we called K over L, and then human capital per worker, which is H over L. And we say that this relationship is given by uh, this function right here that was empirically justified, meaning they have technology levels, they have physical capital per worker numbers, they have human capital per worker numbers, and then they use Chinese and Indian economic growth data to come up with the parameters for this function, which are zero point 0.4 and zero point 0.6. Very nice. Okay, so this kind of gets into what's called the Cobb-Douglas function. So the Cobb-Douglas function is a very famous production function for our case. It's also used in a lot of different other sources of economics. Currently, in my research, I use a version of the Cobb-Douglas function, which is actually a function of wage, and it looks something like this, okay, where K, X, and Y are variables that I'm interested in. So the key defining factor of this production function is you have your two inputs are multiplied by each other. They're both raised to an exponent, and we generally like the exponent to equal 1. So as you can see, we have zero point 0.4 plus 0.6 equals 1. And then typically we throw something in front. In this case, it's technology. Um, so yeah, so again, Y is output, T is technology, K is capital, H, C is human capital, or in this case, we are just abbreviating that by calling it H. L is the labor force. And then how do these 0.6, 0.4, where do they come from? Well, 60% of productivity growth from human capital divided by labor. This is why this has a 0.6, because we determined if our GDP per capita grows by 1, 60% of that is due to human capital productivity growth, and then 40% is due to the capital level. Okay, so that's where the 0.4 and 0.6 come from. Very nice. So why is this a production function? Well, it tells us productivity, tells us the GDP per capita in our example, given the inputs. So it tells us that growth comes from change in these inputs. which tells us where we should kind of invest if we're an economy. So here we have a table here. We are given a whole bunch of variables of human capital and capital per labor, and then we have this investment here over the years, and we want to look at like what is the best level of investment, where should we invest our money? Okay. So, using this information, these economists tried to explain why China grew faster than India between 1978 and 2004. And about half the difference was due to China's higher levels of investment spending, which raised its level of physical capital per worker faster than India's. So this investment spending was investing in factories, investing in tools for our workers to use. And then the other half was due to faster Chinese technological progress. So not only are we buying a lot of tools and making these factories for our workers to work, but also we're improving that technology so they get better tools year after year, which only increase productivity. Okay, so a key thing about this function we're looking at is it has diminishing returns to physical capital. So an aggregate production function exhibits what we call diminishing returns to physical capital. This occurs when holding the amount of human capital and the state of technology fixed, each increase in the amount of physical capital leads to a smaller increase in productivity. What do we mean by this? Well, let's just plot total productivity divided by worker here, and then we will uh, plot capital over labor, okay? And then what this kind of says is when capital labor is really small and when we increase it, we see big jumps at first. But once we keep increasing this capital labor over time, it kind of tends to flatten out in a way. So diminishing returns means you kind of have this, if you're comfortable with math, this is what we call like a concave shape. Whereas capital gets bigger, Y over L increases, but it increases at a smaller rate. So in this hypothetical example, we kind of see this trend of what I just drew. So we have real GDP per worker, and we have physical capital per worker. So we see the first 15K goes a long way because we get plus 30,000. Now we're going to increase it another 15K, and we see this only increases the real GDP per worker by 15,000. And if we increase the physical capital again by 15K, that only increases our real GDP per worker by 10,000. So this is like in that example, you kind of see it. Here it is graphed, which is similar to what I drew. So yeah, so as physical capital per worker rises, real GDP per worker increases, but it increases at a decreasing rate, or another way to say that is the increase and real GDP per worker becomes smaller and smaller as physical capital keeps on increasing. So if we stretch this, we would expect this to flatten off eventually or get really, really, really small. Um, so what about natural resources? In contrast to earlier times, natural resources are much less important when determining the productivity than human or physical capital for the great majority of countries in the world. So some nations with very high GDP per capita, like Japan, have very few natural resources. Some resource-rich nations, such as Russia, Russia has a lot of oil. They're less prosperous. Prosperous. I feel like I'm saying that wrong. Anyway, why is this? Because of trade. So if I need oil, I can trade with Russia and get it pretty easily. If I don't have gold and I need gold, I can trade with a country and get it pretty easily. So it's not as much of a barrier. Now, back in like the 1800s, this was a massive barrier because trade still existed, but it took a longer time. We didn't have planes that could fly in all these resources. The boat system was not as fluid and good as it is today. So sometimes you would order maybe gold from Europe, and if you're in the United States, and then the boat would just never get there. The boat would get lost, or maybe they just said it's actually not worth it to do it. Now you can do this very easily, and the boat will get to you in a month or so, no problem. So natural resources, while they may be a little bit important, they're not as impactful as what they used to be. This is also kind of due to like techno technology growth. So what does determine growth? Well, like I said before, three main components that we're going to focus on is physical and human capital, along with technology. Um, so other things that may impact growth could be property rights, which is the who owns what, contractual rights, and rule of law, and also democracy. So the government can kind of intervene in specific ways that can determine how fast an economy can grow. They can make it very tough by having a bunch of these rigid regulations. They can make it really easily to produce things by having very little regulations, and then everywhere in between. You also have property rights, contractual rights, rule of law. All these things are good. They're important to kind of note, and a bunch of economic papers have looked into this. However, for our class, we're going to have a very simplified model where we only look at these three factors right here. So in this graph, we have aggregate production function. We are looking at what happens when we increase the physical capital per worker, real GDP, similar to what I showed you before, where we have these diminishing returns. This is kind of generally what all these functions are going to look like, where they're going to increase a lot at the beginning when you don't have a bunch, but then once you get a bunch of, in this case, physical capital per worker, it'll still increase, but at a decreasing rate. Okay. So how does technology impact this our productivity? Well, it kind of just boosts the whole thing up. Okay. So again, we have physical capital per worker and real GDP on the Y. If we go back to our formula looks something like this, where I think we decide on 0.6 and zero point 0.4. Okay, so we're graphing this where we're holding H over L constant. So we don't even need to think about what's going on with that. K over L is, I flip slides, hold on. K over L is the physical capital, so that's on the X, and then Y over L is the real GDP per worker. And all we're doing is say we're changing technology right here, and it goes from 1 to 2. So when it does that, what it's going to do is it's going to shift up this entire graph. Okay, and this kind of makes sense. So given we have a lot of physical capital per worker, say there was an update to a software system that makes it so much easier for everybody to produce a whole lot of goods. All that's going to do is if you have 60,000 physical capital per worker, instead of producing 60,000 real GDP per worker, now everyone can be more productive. So now that number can jump up to 120,000. Okay, so essentially all this is doing is it's just taking a number, and then where it tracks, you just you double that number, and it does that the whole way. Okay, let me erase this line. Nice. So why growth rates differ? So there's a number of factors that influence differences among countries and their growth rates. Most of these are government policies, are institutions that alter. So savings, investment spending, foreign investment, education, infrastructure, research and development, political stability, and the protections of property rights. I can touch on a few of these, but if you have a lot of people saving and investing, that can maybe lead to a lot of investment into capital, which can be a good thing. Alternatively, it can mean that people are saving instead of buying your good, which means you want to produce less. Uh, Foreign investment, if you have money coming in from another country, this will only increase your GDP per capita because they're investing in capital or technology for you. Education increases human capital, infrastructure makes everything a lot easier. So the roads are a lot better, which means I can distribute my product easier, which means the productivity of those truck drivers has increased. Research and development, political stability, protection of property rights, all kind of, you can paint a similar story for that. Okay, so let's look at the GDP per capita on the Korean Peninsula since 1950. 1950 was the end of the Korean War. Okay, so the Republic of Korea is South Korea, and then the People's Republic of Korea, that's what we would know as North Korea. So you can see um, a big difference is obviously South Korea's GDP per capita increased a lot. The Democratic People's Republic of Korea did not. This is, because of their obvious political situation. Also, there was a bunch of sanctions that were put on them, and they kind of became an isolationist country, which really limited a lot of their tools towards to increasing their GDP. Simply, some of that was on their fault. Some of that is they just did not have access to that, so there's nothing that they could do. Okay. Success, disappointment, and failure. Okay. Don't fail your midterm. I expect minimal disappointment, but a lot of success. Okay. So the growth rates of economically advanced countries have converged, but not the growth rates of developing countries across the world. So this has led economists to believe that there is such thing as a convergence hypothesis, which fits the data only when factors that affect growth, such as education, infrastructure, favorable policies and institutions are held equally across countries. So the convergence hypothesis says that economies with low per capita income grow faster than economies with high per capita income. Okay. The convergence is that everyone kind of catches up to the very developed nations eventually. Okay. So here you look at the convergence among wealthy countries. So real GDP per capita, an annual growth rate from 1955 to 2008. So this is again an average right here on the Y, and then you have real GDP per capita in 1955. So where were they in 1955, and are they essentially catching up and converging to, the United States, the Canada, the UK, even Australia? And you do see like this downward trend here, meaning when you start off with low real GDP per capita at the beginning, you're going to grow a lot faster to help you converge to GDP of like the United States, of Canada, blah, blah, blah. Um, so this works very well for what we call like wealthy countries. Um, for the rest of the world, it's a little, you kind of see this in a way, like you could draw like a line, but then you see Africa is way down here, even West Asia, Latin America, they don't really fit that bill altogether. If you look and you piece it by country, it fits less well. So this is kind of the convergence hypothesis. What's important here is we have education, infrastructure, and these favorable policies and institutions are held equally. We assume in these wealthy countries, they're held equally, but not in the entire world in general. Okay, so that is all we have about growth. Now we're going to go through a couple exercises like we always do, and then we'll wrap it up. So in this first exercise, we're talking about labor productivity. What do we have on the graph? We have labor productivity on the x-axis and GDP per worker, which remember we talk about Y over L. Um, on the Y, this is physical capital per worker, so this is K over L. So suppose the economy is currently at point A. We're right there, sweet. And then they add 100 units of capital per worker and move to point B. So again, all this is doing is we're adding more units of capital. So we just go from A to B. We're not like shifting up in any sense. There's no technology shift of any kind. We're just adding more physical capital. Um, will adding another 100 units of capital per worker lead to the same increase in productivity? Explain why or why not. Okay, so if we increase capital again by 100 units, that'd be going from B to C. Okay, and then the question that they're trying to ask is this jump the same as this jump? And the answer, just by looking at the graph, you can say it's no. Why is it no, though? It's because we have this diminishing returns. Returns to physical capital. So, like we talked about before, as you add more physical capital, it's still helpful. It still helps GDP per worker increase, but it increases at a decreasing rate, meaning when we go from 500 to 600, maybe that helps us by 100 units of GDP per worker. When we go from B to C, that may only help increase by 10. Okay. You can see it from this graph too, and how it has this shape like that. Okay. If you had a shape that was more like this, then you'd have increasing returns to physical capital. So that would tell a different story. But that's not how we've modeled it. And empirically, that does not seem to be the right approach. So, like our convergence hypothesis that we talked about would be maybe the United States is at point C, and Japan in 1955 had really high growth rates because they went from A to B, but as they accumulated more physical capital, they've slowed their growth rate to approach the United States. Okay, so same graph, but now we are at point E. Very nice. Boom. And we're saying if population rises faster than the economy adds capital, what would correspond to a movement, or what that would correspond to a movement to which point? Okay, so where are we moving? We're at point E. Now let's see, we have the population rises faster. So on the X, remember this is GDP per worker, so this is Y for labor. Physical capital per worker is K for every labor. When the population increases, this means that the labor force should also increase. And specifically, it's going to increase faster than the economy is going to be able to add capital, meaning that this labor will increase, but this capital is not going to increase at the same rate. So we are not going to be stuck. We are not going to be at point E. So let's, for example, say that K stays the same. What happens when L increases and only L increases? Well, that means this entire K over L will decrease. Okay. So this means we go from point E to point D right here. So the movement would be from point E to point D, where the physical capital per worker has decreased. This makes sense because we have a lot more people, but we haven't updated all of our equipment and given them all the tools of the physical capital that they need. So everyone's kind of working with less. And we would expect because of that, the GDP per worker should also decrease. Again, you can kind of see this if you increase L here, then this whole thing should decrease. That's what we find right here. All right, very nice. So in exercise 3 here, We're still looking at the same graph, so it's helpful just to put all these labels. Y over L is the GDP per worker, and physical capital per worker is K over L. In 2010, the United States was at point A. Very nice. Maybe draw like a little star there. In 2011, they were at point C. So this is 2010 and 2011. We jumped up to this guy up here. Okay, what fraction of the growth rate in labor productivity from 2010 to 2011 can be attributed to improved technology? Okay, so remember, if technology is the same, so if we are in 2010 technology and we are at this point right here, meaning we have physical capital per worker of 200, we should expect to be at point B. Okay, so the increase from 500 to 600, that has nothing to do with technology. Okay, but because technology increased, we are not at B, we are at C. So then 800 minus 600, which is 200, is the growth in labor productivity that is improved technology. So this growth in 200 GDP per worker is the answer that we're looking for. Okay. So again, with this question, in 2010, we're sitting at this point, and then the other point that we observe is 2011. Okay. We don't observe this point right here. This would be if we increase physical capital per worker, but we are still in 2010. Okay. So two things shifted here where we increased the technology and we increased the physical capital per worker. If we had the same technology, we can estimate we'd be at point B. And so the difference between point C and point B in terms of GDP per worker is 800 minus 600, which gives you 200. Okay, and that is all that we have for today. So that is the first lecture of the week. I will be back with part 2 on Wednesday.